Started. I'm Leah Medeiros. I'm going to be your host for today's webinar, and I want to thank all of you for coming to today's webinar, which will be focused on handling data and managing errors. Today's session is the second in a series designed to prepare participants for the summer school. Please also register for the VLBI data series webinar, which will be on the PIRE Black Hole PIRE website as well. We will be adding a few links to the chat. So if you don't have any of these links that I will be mentioning today, please do check the chat. The Black Hole PIRE Summer School will be held from August 3rd to 7th in Puebla, Mexico. More information will also be available on the Black Hole PIRE website. All past webinars are available on YouTube. At the Black Hole PIRE Science channel. Again, we will be adding a link to that as well. Today's webinar will last 1 hour, and that will include time for questions. And one of the very important things that I want to ask all of you to do is to please fill out these surveys at the end. These are super short surveys. They're only a couple minutes, and your feedback is incredibly important to us. We do look at all of those surveys, and we do try to take everything into account so that we can continue to improve the webinar series for you guys. A few other housekeeping things that I wanted to request is that everybody please turn off their audio so that we don't have background noise. And we'd also suggest turning off your video because that might improve the bandwidth for you. For questions, I've talked to Lindy. He's totally fine if you'd like to ask questions during his presentation. I'll be keeping track of the chat, so please add questions to the chat if you have any questions throughout his talk. And there will also be question and answer at the end as well. So I would like to introduce Lindy. So Lindy is a radio astronomer and EHT data scientist at the Harvard-Smithsonian Center for Astrophysics. He leads the calibration and error analysis efforts for the Event Horizon Telescope toward the goal of obtaining high-resolution images of supermassive black holes. Lindy obtained his PhD in physics from MIT while working on the LIGO experiment and was a NASA postdoctoral program fellow at Goddard Space Flight Center, working on searches for high-energy counterparts to gravitational wave detections with the Fermi telescope. He has a general interest in black holes, experimental general relativity, and the application of statistical methods and modeling for precision measurement.
Okay, thank you, Leah. So I'll get started. It's great to see a lot of new people I don't know on the list of attendees. So thank you for joining. I'm going to share my screen here. So let me know if this has a problem. So I'll be talking about VLBI data and errors. I spend most of my time processing VLBI data and thinking about how to reduce it, calibrate it, and interpret it. So I do work with the Event Horizon Telescope collaboration, and many of the examples I'll draw from deal with things that are related to EHT data. But my talk is not specifically focused on how to process EHT data. It's also not focused on particular tools and sort of recipes, but I'm hoping to give sort of a broad overview of understanding what's included in VLBI data and what we want to think about when we process it and interpret it. So there are many great resources, and I think we need to start with listing some of them. Of course, many of you probably know Thompson Brand Swenson's basically Bible on VLBI, all aspects of VLBI. So this is a great resource for all levels of expertise, and you know, each time I read it, I learn something new, or if I've been working on a project or problem for many months and find a solution, usually I'll eventually realize it was in this book. There's also a written series of lecture notes. This is from the early 90s, but this is from NREO's summer school, but also a very long and comprehensive collection of notes. A similar set of notes prepared by KVN. I don't see these KVN lecture notes publicized as often, but I think they're extremely nice pedagogically. So they explain a lot of things from the ground up in sort of a modern way, and I think people would get a lot out of taking a look at those. And then the imaging workshop run by NRAO also publicizes their slides from presentations every year, or every year that they run. And those are also a very nice resource to use, and they're online. Okay, so just a review of what we're recording when we look at VLBI data. So I think this was all shown in previous presentations, but it's good to revisit. So what we're gathering when we record at multiple telescopes around the world and then correlate the data from each telescope is something that we hope to represent the spatial coherence of the wavefront. And that's related to the brightness distribution of the source that we're observing. So here I have shown just a point source, which is the simplest thing we can look at. And the interesting property about a point source is that the wavefront is perfectly spatially coherent along the plane of propagation. So in the far field, we're expecting plane waves, and we expect the exact same signal at each telescope. So here on the left, I've shown sort of a diagram of the point source, and then on the right, the expectation value of the coherence of the electric field between the two receiving telescopes. And that should give you an amplitude that's just the flux density of the source. Okay, so one experiment we can do, so this is taken overhead, and we can just shift the source a little bit on the sky. That imparts a very small geometric delay, which translates into a phase delay of one of the telescopes with respect to another. And we can write that here and take it in terms of the projection of the vector between the source direction and our baseline between the two telescopes. And here the baseline is written in units of wavelength, observing wavelength. So this phase offset will scale with the frequency as well as the displacement of the source. And then if we think about an extended source, you can really just linearly superpose many point sources to fill out an extended source with structure. And so the extended source now interferes essentially all these linear point sources in such a way, and now we're integrating over a brightness distribution over the sky. So if you replace this I sub nu with a delta function for a point source, you recover one of the previous equations. But you can see that we can simply just integrate over the interference created by an extended source to get the coherence between two element array. So what we've recovered here is the visibility function as a function of essentially the baseline U that we have on the ground. And we're measuring then the complex correlations of all possible orientations of these two elements. And these measurements encode the sky brightness distribution of the source. One thing I didn't cover, so this was all taken at zenith, just completely overhead. If we do have a source off at an angle, what we have to do then is project onto the plane of propagation. So our baseline vector now from 1 to 2 is just projected into something that's perpendicular to the line of sight to our source. Okay. So what do we need? What are ingredients for VLBI specifically? What we need to do to get sort of a complete picture of our source distribution is just measure the electric fields and their correlations at various locations along the plane of propagation. But this is difficult for a number of reasons. The first reason is Earth is round and moving. So we don't measure directly in the plane of propagation. There are various effects due to just the positions we put our telescopes in and the velocities that they're traveling in. So this also imparts Doppler shifts on our measurements. There are irregular delays from the atmosphere, the troposphere, and also lower frequencies, the ionosphere. So this also distorts the signals at each telescope in different ways. So this needs something that makes VLBI measurements particularly difficult. There are different amounts of noise, so we're not just receiving a signal. We get a lot of We get a lot of energy from radiation from the atmosphere, from receiver thermal noise, and this is different at all the sites. So this is a major component of what we actually measure in terms of the correlation coefficient. There are various electronics and path delays, so there are many cables. There are many other sources of path delay and dispersion, so differential delay with respect to frequency along the receiving elements. And then we need to timestamp all this data, and VLBI includes intercontinental baselines. We can't connect it all up with a single clock reference, so what we have is independent clocks at all sites, and these are typically very stable atomic clocks, but they're still independent. They're imperfect, and there's some aspect of clock error just from our clock reference that we're using at each station, so that needs to be accounted for. There are post-digitization artifacts, so these are particularly hard. This is stuff that can happen to the data after it's digitized. And everything upstream to digitization, if it impacts the data, it's something that needs, in some sense, to satisfy the laws of physics. After digitization, you can almost do whatever you want with the data. So if something happens with data after digitization, it can be pretty hard to disentangle. And finally, unexpected data issues. So VLBI, I don't know how many of you have observed, but it's over a period of time. Many things can happen. Things aren't stable. So we're processing many scans of data, and we have to be careful that things don't show up that we didn't expect. Okay, so what's our job as people who reduce the data, calibrate the data? What we want to do is essentially mitigate as many of these artifacts as possible. I call this, ingest, where we have to hide as many of these effects as possible. But we do have to be careful while trying to simplify the data this way. We don't want to ruin the data in terms of its interpretability. So we have to do it in a very careful way. Okay, so I've drawn a diagram here trying to represent the basic data pathway for VLBI. And these are represented in terms of the steps, and I'm thinking particularly of an EHT data reduction here, where we're taking a huge volume of data. So the raw signals we acquire, the telescopes all added together over the course of a campaign is something like petabytes of signal data. These are taken to central correlation facilities. That's where the data are correlated. We're measuring the correlation coefficients between antennas. This is, in some sense, forming the virtual mirror of our telescopes. At that point, it's averaged down. It's also translated into baseline correlation coefficients, and the correlator produces something like a terabyte of measurements. Calibration stage, this is where we're trying to fit out the systematics of the data. So we're trying to fit out many of the models for the environment, for the instrument, so we can simplify and further average the data. And this is what the talk is mostly about today. And here's just a picture of some complexity from atmospheric phase in red. So if we can, over 3 baselines, fit these out, we can simplify the phases, average it through in time, and bring the data down from terabytes to something like megabytes that we can pass on to analysis. Finally, analysis, we have things like imaging. We might have things like just estimating the mass of a black hole or something. This is our inference problem, where we're trying to solve something about our source itself. And typically for the EHT, we're thinking of simple sources, and we're really not fitting that much source information compared to the level of complexity that came previously. So any amount of simplification we can do upstream makes it much easier to do this downstream analysis. Okay, looking a little more concretely at what we have at some of our stations, and I figure this is pretty representative of a VLBI station. On the left here is EHT's backend. This is at Pico Valletta in Spain. So you see mostly all these recording devices with many hard drives on the left, but also our digital backend chain. So I've diagrammatically put a receiver and down converter on the right. You have something like the sky signal in a narrow bandwidth around our observing frequency coming down and being converted to baseband. So it's being down converted to something from DC, 0 hertz, to our recording bandwidth, which is something like a few gigahertz. Also on this diagram, just below it, I've drawn sort of a simplified diagram of how the signals themselves are getting added together and transformed, both in terms of the source signal and in terms of noise contribution. So here I have the source coming in with some transfer function. This is in terms of frequency, so there might be some transfer function applied to the source signal, and then some system noise being added to it. And in our case, the system noise really dominates the signal in terms of signal power versus a source itself. One aspect of the data, of course, is that it's digitized, so it can be stored on hard drives. We recover most of the information with very low bit quantization. So this is an example of quantizing the original continuous data down to 2-bit digitized samples, Nyquist sample. So this is the rest of the signal chain here, and this imparts some quantization noise to the signal. So if you think about the middle and bottom time series here, you can add a little bit of quantization noise to the middle trace to get the quantized signal. And for 2-bit data, that's about 12% of noise power. So you can think of it as an extra component of noise added that's independent across all stations to the signal before recording. Quantization noise itself is a little bit hard to understand, but there's a nice trick to solving the amount of quantized noise and also the spectral distribution of quantized noise. But this diagram on the right is supposed to help with that a little bit. You can see the original unquantized signal in terms of this band pass, so 0 to 0.5. That's original baseband signal. Quantization, of course, introduces, if you think of it as a step function now in these 4 levels, of a lot of high frequency noise and some distortion to the signal at low frequencies. And when you Nyquist sample that, you fold all that noise back into the baseband signal, and it includes that sort of 12% correction I talked about. In this case, instead of 2-bit, I showed 1-bit because it showed the effect a little higher. So there we're thinking of something like 30 some odd % extra noise. So I did represent the signal chain. This is essentially is the bandpass that's going to be applied to the signal and the noise. And there are 2 important bandpass effects. So this is something that's important to remember when you're trying to unwind what happened to the signal. There's, in my diagram, H and G, 2 different bandpass effects. One affects both signal and noise, and one was affecting only the source signal itself. And sometimes this is factored into a real and complex bandpass during calibration. And the real bandpass has no phase information. So the reason we split that out is because we don't really care what happens to the phase of noise. It's just independent. And that you can derive from noise-dominated autocorrelations of your signals. Complex bandpass, something that requires a signal, requires us to measure a signal, needs to be derived from complex measured correlations on actual source data. So you need something like bright calibration sources to tease that out. Also, what I didn't describe here are nonlinear effects. So all of these are transfer functions. So they're assuming some kind of linear process, but they're things like delay rate, stretching or compressing the signal, things like atmospheric phase. These are all time-dependent factors, and so they're not described this way, at least not on a very long time scale. They'll need to be broken down into a much shorter time scale. So any kind of frequency shifting, even down conversion, is not described here. Okay, so one thing that is very important to consider when we're talking about the propagation of the signal toward our measurement is how the signal is being manipulated by so-called gain factors. So here we have the electric field, and now I've taken it parameterized in time and frequency, and all these instrumental effects and atmospheric effects and environmental effects can be wrapped up into something that affects the amplitude and the phase of this parameterized signal and electric field. So we've wrapped this up into a complex gain factor G. We multiply it by original signal E, and we get the recorded voltage data at our antenna. So this is on a station-based. This is station by station. When we take something like an ensemble correlation coefficient, we can pull out these gain factors. They're just constant values here, or some kind of function of time and frequency, but varying slowly. Pull them out and represent the correlation coefficient we measure to the actual visibility. So on the right, the ensemble expectation value of E1, A2 is our source visibility function. V1, V2 is going to be the correlation we measure in the two recorded signals. So that, as I mentioned, the signal and the ensemble averages here are both parameterized in time and frequency. So an underlying assumption here is that G is in some sense varying relatively slowly, so it can be pulled out of these ensemble averages. There is a very nice matrix formalism when we're considering two orthogonal feeds of an antenna. So this is a typical case if we're measuring something like a left and right circular polarization. So here I've shown the same equations, but with both polarizations, in which case you also have cross products between polarizations. And these gain factors just turn into diagonal matrices here for both the first antenna and the second antenna over the baseline. And when you use this, you can represent these in terms of Jones matrix formalism, and this builds out into the measurement equation for radio interferometry. So here we have the same equations written in a matrix form, and instead of one gain matrix, we've stringed together a product of Jones matrices that each represents some physical process in sequence as a source is emitted toward measurement. Oleg Smirnov, 2011 paper is a very nice introduction to this formalism. Why do we split out all these matrices? And so there's a general principle of what you want to think about when you build a calibration model for the data, is that by splitting out this way, it might seem more complicated, but it actually lets you simplify your calibration model, because each matrix here is going to represent a physical effect. And if you're thinking about how to parameterize those in as few parameters as possible, it helps to split them out. So some might be independent of frequency, some might be independent of time, some might have a certain parameterization, like be smoothly varying. So you split them out and you can describe each as simply as possible. One thing to keep in mind, though, when they're all split like this, is that the matrices don't necessarily commute. So they're not all diagonal. Some things like leakage or change of polarization basis has off-diagonal terms. So the order in which you apply them is actually pretty important, and you need to make sure that you're consistent about that order. So the whole structure, you can see these nice simple equations here with the matrices. It's very useful for bookkeeping, but it's, you're still responsible for adopting good models for all the matrices. So just because you've done nice simple bookkeeping doesn't mean you're absolved from trying to parameterize a model simply and, well, of course, accurately. Another thing I haven't talked about on this particular slide is how the noise is tracked. So this is all signal propagation, what happens to the signal. And if, as you recall from the previous slide, noise is injected at some point into this process, and it'll be subject to all the amplitude factors that then occur in the signal chain. Okay, so we've talked about gathering the recorded signal at all the antennas. All the data are then sent to the correlator. And what the correlator is doing is it's aligning the signals as best it can in a plane of propagation using these time delays I've represented here, and then forming all the cross correlations between pairs of antennas. So the cross correlation here, it's a very simple equation. It's just the expectation value of the product of the signal of two antennas normalized by their noise power on the denominator. And then here I've included this eta quantization factor, which is pulled out of here to represent that added quantization noise that I showed in the previous slide. Things the gain factors that I mentioned earlier will fold in then to the signals measured at each of these sites here on the numerator here of the correlation coefficient. So something that affects the correlation coefficient measured. So something like the atmosphere will impart a station-based gain term onto this numerator. One thing to keep in mind is that the correlation coefficients we expect to see for real sources in VLBI are very small. So they're so small typically that we're using units of 10 to the minus 4 to characterize them. So they might be 10 to the minus 6. This is because our signals themselves are very noise dominated in power. So especially when you're considering a long baseline where the correlated flux is very small, the correlation coefficient is going to be very small. So to make a measurement in this very low sort of signal to noise power regime, we need to average many samples. So just in this particular case, maybe 10 to the 8 samples for detection. So if you're thinking about integrating a gigahertz worth of bandwidth, maybe you need to integrate for a full second to actually see something, or many seconds to actually see something if the correlation coefficient is sufficiently small. Okay, so we have a correlation coefficient. I'll take a little diversion to talk about how this is related to correlated flux density of our actual source. So the correlation coefficient is a normalized quantity. So it's the correlation normalized by the noise power. If we want to relate this to actual correlated flux density, we need to know what that noise power is. So we wrap all this up into a quantity called the system equivalent flux density at each site. And that's supposed to represent the noise power in the site, or the sort of the system noise, in units of flux density from an astrophysical source above the atmosphere. So it's accounting for all the effects of say, attenuation through the atmosphere. So this SEFD here on the right is representing these noise power terms in the denominator of the left equation. And then we can take our Rij, the correlation coefficients, into Vij, which are our complex visibilities in physical units. Oops, sorry. SEFD itself, there's something of an art to estimating it. So I'm not going to go into this in detail, but it's some combination of using first principles. So we have an idea of how much energy is being captured by telescopes and how efficient those telescopes are. We look at bright planets of sort of known flux. And also we can put noise sources in front of our detectors and calibrate them that way, or block the source. So from all this, we derive some estimate for the a priori sensitivity of each site. High frequencies, these estimates aren't very good. So they might be good to about 10%. So instead of an absolute calibration, it's maybe good to think about this as some kind of prior on the calibration, which can then be refined later on. Also for something like the EHT, which has many different telescopes of different, say, sizes in different environments, the SEFD here can range by orders of magnitude. So maybe from 100 Jansky to as much as 10,000, or even approaching 100,000 Janskys. So they're wildly different sensitivities at the sites. So this is a major thing to consider when interpreting a physical model into the data. Okay, so that was amplitude. There's also a phase term. So I wrote the same equation, but I added back in the phase terms here. These theta 1 and theta 2 are station phases, so very small delays of each site with respect to another. Classically in interferometry, maybe you could calibrate these phases by looking at a nearby calibrator target of known structure at high frequencies. So if we're talking about something like the EHT, this is pretty much impossible when there are very few calibrators to use, and two, the atmosphere is jittering these phases very rapidly on the scale of maybe 10 seconds. So over the course of minute-long scans, it's pretty much impossible to do any kind of phase transfer. So we're essentially going to assume we have no a priori information about the station phases at each site. But that doesn't mean we don't have any phase information in the array. So we have order n squared baseline measurements of phase across all pairs of stations, yet we have n minus 1 unknown station phases. So there's some arbitrary phase reference, so that's where the minus 1 comes from, but essentially n minus 1 unknown station phases. So the baseline measurements that we do make do capture some structural phase information about the source. It's just wrapped up in this sort of complicated fashion. So we can see this. We can actually show that the information is captured by what's called the closure phases. So if we have a closed loop, in this case a closed triangle across 3 elements in the array, we can add up the phases over these 3 baselines and cancel out the phases due to station-based phase terms. So these thetas on the top, if you add them up, you'll get a theta 1 term from one baseline and a minus theta 1 term from another baseline. So those will cancel out. Structural phase will be, in some sense, preserved by this, although in a complicated way. But these closure phases are independent. They are insensitive to the relative phase of each antenna, but by implementing them, we do subtract n minus 1 degrees of freedom, phase degrees of freedom from the baseline. So those correspond to the station phases themselves. And with respect to a perfectly calibrated array, the closure phases, and there's a similar prescription for closure amplitudes when you have unknown amplitudes, capture some fraction of the information exactly corresponding to this ratio, accounting for the missed degrees of freedom. So as the array grows and grows, because there are n squared measurements and n unknown station gains, you recover more and more of the fraction of information, even without calibration. Okay, so a big part of the act of calibration, and in particular phase calibration, is that it allows us to average the data down. So you remember that first slide where we were going from terabytes of data from the correlator to maybe megabytes of data after averaging. But there are limitations to these averages. So first we could consider what are the limitations to averaging just from the source itself. So here is the Van Sitter-Zernike theorem again, showing the way ensemble averages could be formed by averaging the signal from the source at each station. For the EHT, we're actually looking at primarily very simple and compact sources, and maybe the field of view is effectively several beams or 10 beams across. That implies there's actually quite a long coherence time scale to the intrinsic source variability over time. So on the left is something like our UV coverage. So tracks are sweeping out these different spatial frequencies as the Earth rotates, and they only sweep through these tracks so fast, and the actual visibility function can only change so fast due to the simplicity of the source. So we're actually expecting over time that the visibility, intrinsic structural visibility over a baseline, to change relatively slowly. So there's not much of a constraint on averaging in that sense. And a similar argument can be made for averaging in frequency. So we have a fractional bandwidth of something like 10%, which is really not, well, it's pretty small compared to the amount of variation we expect from our source itself, from our compact sources itself. So the takeaway here is there's not much of a constraint on averaging for the EHT, at least, due to the variations in the source model visibility over time or over frequency. And this is important for calibration if we want to make some assumptions about the intrinsic smoothness or stability of the model visibility without making very strong assumptions about the source itself. So just by making some assumption about its compactness, we can make assumptions about the changes in the model visibility without actually assuming a particular source structure. Okay, but what about the gain parameters? So the gain parameters, unlike the source model, do can potentially vary quite rapidly. So one of the first ones we worry about are first order parameterizations in phase. And sorry, let me, Zoom is covering up a few of my slide elements, so it's making it a little hard to present. So I'm going to have to move some things around. Okay, so gain parameters. So here, G1 and G2, of course, are complex gains, and phi here I've taken as the phase of those gains on the right. So if you expand this into how phi is going to change as a function of frequency and of time, of course, G, those gain parameters from the previous slide, are functions of frequency and time. You can take the first order effects, and these represent, so each of them represents the evolution of phase due to delays, relative delays between the two elements over this baseline, one in station 1 and station 2, and also delay rate, which is something like a Doppler shift or stretching or contracting of the signal over these of the one station with respect to another. So I've written these here, and this is something like first order phase variation with respect to time and frequency. Here are a couple diagrams to help understand how these play out in terms of the data. So in blue and red, you can think of this as a sort of a quasi-monochromatic signal from each station. And station 2, let's say that's the red signal is delayed with respect to station 1. And the delay imparts a phase offset. And the phase offset actually increases if you increase the frequency, even if the delay is fixed. So the phase offset of the bottom plot here is quite a bit greater than the phase offset of the top plot. So that's what you see here in terms of the functional form of the delay. It causes increasing phase offset with respect to frequency. Now the delay rate, as I mentioned, is like a Doppler shifting. It's a stretching of time. So what this gives you is an increasing phase shift with respect to time, accumulated time. So you see here on the bottom, the very bottom plot now, the station 2 with in red is accumulating or lagging behind station 1 due to the stretching of time. So it's slightly slowed with respect to station 1. Now this effect also scales with frequency. So if you assume everything is happening faster here, then the phase accumulation will occur more rapidly, and that's why you see the frequency term in the formula for delay rate. So these effects actually can be quite large when you consider the Earth model, the Earth geometric delays as far as Earth rotation. But these very large delays and rates are taken out at the correlator using a very accurate a priori Earth calibration or Earth model. So Earth geometric model, and also includes some atmosphere path delays. So this model is called Calc. You may have heard of it. It's done at the correlator at a very high time frequency resolution on the data before the correlator averages and dumps the raw data out. So the calibration stage, we only worry about residual clock errors, so things that aren't included in this model. The model is a priori, so it is going to have some residual error. And we can look at the limits of what these systematics can be given the correlator dump time and the correlator dump bandwidth. So this is how much the data have been averaged at the correlator. For UHT, is something like half a second of time averaging and maybe half a megahertz of frequency averaging. And this gives us some limits on the rates and delays we can accommodate. So post-correlation, we may be able to search over a delay of about a microsecond and a rate to within about 2 picoseconds per second, or about 1.3 millimeters per second. So this makes a lot of sense. If you look at this dump time in seconds, 0.5 seconds, our wavelength is 1.3 millimeters. So if you want a Nyquist sample changes in those wavelengths, we can accommodate about 1.3 millimeters per second of change. Okay, so so how do we take out these effects, both these residual linear phase effects as well as nonlinear effects? So this is a process of fringe fitting, and this is, probably, well, this is the most important reduction. Well, this is the most important part of calibration reduction to get right if you want to be able to successfully simplify and reduce the data size. So I describe fringe fitting as essentially self-calibration of residual clock errors. From that, we extract our correlation coefficients. And at high frequencies, there's not just this linear trend of delay and delay rate, there are also nonlinear effects. So I've put these diagrams here to try to show what's happening to the data as we correct for these different effects. And on the left, you have, say, a correlator output gridded up in time and frequency. In the middle panel, you have the FFT of this data on the left, and it's showing the fringe pattern you expect. So it's, if you do a correction for a certain delay and a correction for a certain rate, you're going to get the integrated power resulting from those corrections. And on the right is just a scatter plot of all the correlation coefficients subgridded on the left with their average. So the first thing we can do is something like correct for a nonlinear phase bandpass across the band. And between from the first step to the second step, you can see that this cleans up the delay quite a bit, and it gives you a cleaner delay fringe pattern because we've taken the nonlinearities out in frequency. After that, we can fit the delay and center it, and that's what you see here, and do the same for rate. So this is then taking out the first order fringe solution, but you can still see quite a bit of messiness in the delay rate from nonlinear evolution in time. So the last thing we might want to do is take out those stochastic phase drifts to the atmosphere and finally get a nice clean fringe solution. We can average the data and make the best measurement of the intrinsic correlation coefficient after averaging. Okay, so these solutions here, I mentioned four different things we can do. This is built out in a phase calibration model and solved for using phase calibration pipelines. So for the EHT, we have a number of custom pipelines designed to build out these models. I won't cover them in detail, but the reason there are these different steps is so they can both implement a simple model, so factoring things out in terms of frequency dependent or time dependent effects, and also utilize as much signal to noise as possible while trying to solve for systematics. An important thing to consider is that while doing all of this, we want to apply station-based corrections and maintain closure, so maintain the ability to factor gains in terms of station-based quantities. Okay, so some things that can go wrong in this entire prescription. One is, I did bring up a number of times that we want a simple model. So one common problem is that we've just used too many free parameters to try to define our systematic parameterization. So one easy place this can happen is, for example, using very short segments and trying to track atmospheric phase. Maybe you don't actually have the signal to noise ratio to solve for atmospheric phase every second or every half second. So what happens if you try to solve for things and you don't have the signal to noise ratio to do so? You can introduce calibration noise. You can end up overfitting your data and biasing amplitude upward, or biasing phase towards an assumed source model. And you end up underutilizing your array constraints and gain priors. So you're underutilizing something like an assumed smoothness about the gain in time if you segment it up in very short intervals and assume no correlation between those intervals. Another pretty common problem is that you're trying to make averages. So we do want to average the data, but we need to make sure that the gains, the residual gains, are stable over those averaging intervals. And if they're not, we can cause trouble trying to average a complex, vector average a complex quantity when there are gain systematics shifting the phases or even amplitudes of those quantities. And besides reducing the coherence of the data, this can also introduce non-closing averages, because we're averaging the product of gains, and those averages might no longer factor. The last one, I guess, a little bit obvious, leaving in bad data. I also said ignoring systematics here. The reason this can be a problem is because we're in some sense, solving for things we almost always just assume Gaussian noise. And if there's a very large systematic from bad data left, you can get a wildly wrong calibration solution because the systematic doesn't fit Gaussian noise at all. So they'll end up driving the solution. They'll be 100 sigma away from your measurement. So assuming Gaussian noise and leaving in a residual systematic can be very dangerous in terms of getting a good solution. So you can mitigate this by, either looking carefully and selecting only data where you're confident about your noise budget, or trying to mitigate this by using softer constraints on something like a chi-squared. Okay, so I will try to, in the remaining time, cover a little bit about noise. So there are various sources of noise and errors. The most simple one is thermal noise. So I mentioned this a couple of times, but this is the statistical error due to the finite averages that we employ to estimate correlation coefficients. And in principle, it's fairly simple. So I wrote here this thermal error on the correlation coefficient R. I didn't include the quantization correction here, but it's just basically derived from the central limit theorem. If you have white uncorrelated noise, basically scales with the number of samples you've integrated in a very simple way. The thermal noise is nice. It's Gaussian. It's independent in both the real and imaginary components. And so it scales very simply as we vector average quantities, and as we scale things by gain factors, the thermal noise just translates very trivially into new quantities. But it is always good to cross-check that you've propagated thermal noise correctly as you're reducing the data. So here on the bottom, I've shown two examples of how this is done. One is taking closure phase differences at high signal to noise ratio and checking to make sure that the errors on those closure phases are within your thermal budget. And another here is a little more tricky. This is using the intrinsic scatter in the data at hopefully low signal to noise ratio and something like amplitude to try to evaluate thermal noise budget. And the reason it's tricky is because a lot of the variability of the source can bleed into this measurement. But these are two techniques. One works at high signal to noise, one works at low signal to noise, and things like these tests are important to validate your thermal error budget at the end of an analysis. Another artifact of thermal noise it is important to keep in mind is that if you translate your data from complex coefficients or complex numbers into amplitude and phase, the errors do become non-Gaussian at low signal to noise ratio because that is an intrinsically nonlinear transform. I probably won't go into it in detail here, but if your signal to noise ratio is falling below 2 or 3, this is something you should watch out for. After thermal noise, there are things that are systematic errors, and I'll talk about two categories of systematic errors. One is closing errors, so this is something like gain errors in your gain terms, and this is reflected here in self-calibrated gain solutions for stations, and this is from the EHE's imaging paper 4. This isn't too big a deal. It is important to keep in mind, but it's a systematic because it's not part of the thermal noise budget N, but it is stationized. So it is an error in these factorized gain parameters. There's something that is a little more nefarious, and these are non-closing errors. This is something we really try to minimize. So this is something I've added on to the baseline as this error term E. So this is often called also a baseline error. And we can check this by cross-comparing data products which we expect to have the same measurement from. For example, closure phases between two different bands of our data set. And we can try to parameterize unmodeled error on a baseline in terms of some systematic contribution. So here I said this is commonly modeled as additional Gaussian random variable, but we do have to be careful if we're assuming those errors are independent from measurement, because they're not always the case. Covariant errors, I think I'll try to go through this quickly, but the more you manipulate the data, especially adding data together, maybe adding things into a closure phase, or multiplying things into the data that are intrinsically, if you're multiplying some parameters in the data that has its own associated uncertainty, you can introduce covariant errors into the data. So the original thermal noise is very nice. It's independent across each measurement. But if you have covariant errors, you need to consider that when evaluating a likelihood or evaluating any kind of chi-square statistic. So your fitting becomes much more complicated in the case of covariant errors. So if you're going to complicate your data processing, you should have very good reason to do that without just simply using independent measurements. Okay, so this is my last slide. So we've done a lot of work. At the end of the day, we've reduced the data, we've simplified it, we've fit out as many model systematics as we can. And we want to make sure at the end of the day we've had good data and not bad data. So we need a validation step. How do we identify outliers and how do we validate our error budget? And so here are just a few examples of how this has been done on EHT or EHT-like data. So one is on the left from the EHT paper 3 on the first M87 results. This is closure quantities and pipeline cross comparisons. So we have 3 reduction pipelines. We do things like looking at closure phase differences between different bands. And also in the middle, this is from GMVA data, so something similar to EHT data with ALMA. Looking at this is now not visibilities directly, but this is the derived delays between right and left polarization, which we expect to be the same if they are correctly referenced. So this can be compared directly against their thermal noise. This is another check. And then baseline delay closure across a triangle. We expect the delays themselves to close on these compact sources. So this is like testing a trivial closure phase, but testing a delay, and we can make sure these are consistent within our thermal budget. And here, everything looks good, but it's not at all uncommon early on in a reduction stage to see for any number of problems to arise and for them to show up as outliers in these sorts of validations. Okay, so that's it. Thanks very much. I was asked to make sure to advertise this survey at the end of the talk. So I'll take any questions.
Hi, everyone. If you have questions, please add them to the chat. I currently don't see any questions in the chat, so please add your questions there. Are people able to see? Oh, there we go. Okay, so we do have a question. Lindy, do you want to just read the questions?
So first one, do you have do you have to care for the ionosphere during fringe fitting? So for the EHT, we don't have to care about the ionosphere. We're looking at a high enough frequency where the ionosphere doesn't affect our phases. So that's typically going to be something that you need to model if you're looking at lower frequency observations and say the centimeter wavelengths. But yeah, the model, systematic model you want to adopt definitely depends on the character of the array and the observing frequency. And so I just demonstrated something from mostly an EHT perspective, but you want to think carefully about what your particular situation is. Okay, so from Angelo, to what extent can you just use the same pipeline from year to year? Do you need to change a lot? So you can definitely use many elements of the pipeline from year to year. I would say we've been building out more and more tools to do so. For the EHT's data set so far has been evolving quite a lot from year to year. So we can't just use the same pipeline. I think we've either doubled the sites, or we've, say, added ALMA, changed the bandwidth, changed various configurations. So it's not push and go at all. There's quite a bit of customization that has to be done. But I suspect if the array becomes stable, then we will be able to use the same pipeline.
Great. Are there any other questions from anybody? Gonna wait another minute in case anybody's typing a question. We do also want to remind everybody to please fill out the survey. Again, it should only take a couple minutes, and we added the link to the survey into the chat as well. We do not have any more questions, so should we wrap it up? Lindy, Rosie, anything else we need to announce?
Nope, that's it, except I would encourage people to watch for updates on the PIRE Summer School that's planned for August. We know that the travel is uncertain right now, but we anticipate that this is going to resolve over time. So please do see the PIRE website for future updates on the summer school.
Great. Thanks again, everybody, for coming to the webinar.
Thanks,
and
Lindy.
Please fill out the survey.
Goodbye.